So, to put all this in words, if we imagine we're looking at the star from above the top of the atmosphere, we see radiation from layers whose temperature increases the deeper they are below the surface. So we're seeing a blend of radiation from layers of different temperatures. Some of it cooler than Tef, some of it hotter than Tef. Cooler than Tef, some are hotter than Tef, namely the ones above optical depth 2/3 are cooler than Tef, and the ones below optical depth 2/3 are hotter than Tef. We're getting radiation essentially from every layer, although as the optical depth gets bigger and bigger, you're getting a smaller and smaller fraction. A layer that has an optical depth of 10, only e to the minus 10 of its photons make it to you, so you're practically seeing nothing from a layer at an optical depth of 10. But a layer at an optical depth of 1, yeah, you're seeing a fair amount of its radiation, a third of it. If you're seeing it at an optical depth of 2, you're seeing like an eighth of its radiation reaches you before it scatters somewhere. So you mix all that together, and the effective temperature you get is Tef, and that is also the actual temperature at the layer which is at an optical depth of 2/3. So the resulting effective temperature Tef is a sort of, this isn't exactly correct to say this, but it's a sort of average temperature of the layers we can see. And Tef is equal to the actual temperature of the layer at an optical depth of 2/3. I'll let you catch up before I keep talking. So, in sloppy language, we can kind of say, so what we see looks like the radiation coming from the layer at an optical depth of 2/3. That's sloppy because we're really seeing this blend, and it's not a perfect black body spectrum because we're blending black body spectra at different temperatures. But in the sense of, what we're really saying is code for all that over there. In rather sloppy language, we can say the radiation we see looks like the layer at tau v equals 2/3. Kind of say it looks like it's coming from the layer at tau v equals 2/3. Put another way, if the temperature wasn't changing with depth, and all the layers had that same temperature as the layer at tau v equals 2/3, we'd be seeing radiation whose temperature was TAF purely. We get black body radiation at temperature. We really see a blend from different layers, and so it looks like it's coming from the layer at tau v equals 2/3, so to speak. Or even worse, because you will hear this, and this is really sloppy. We see to an optical depth of 2/3. But we don't. We see well below that. But it's as though what we're seeing kind of looks like it's coming from the layer at an optical depth of 2/3 when you blend everything together. So sometimes we sloppily imagine, oh, we see to an optical depth of 2/3 as a simplified way to put things. We see to an optical depth of 2/3 along the line of sight. Tisk after that, as in, that's really sloppy, but you'll hear that, and I'll even say it, but just remember that's sloppy. It's not, it's a very incomplete description of what's really happening. The other thing is, we'll use this as a rule of thumb even when the assumptions, which they never are, aren't satisfied. It's not a bad approximation even when you don't use the Eddington approximation, etc., etc. We'll use this as a rule of thumb even when our assumptions are not fulfilled. So let's stop there and take a break, and then we'll use that to understand where absorption lines come from, and so on and so forth.